because the stress analysis, either the stress or either the shear stress. So all of the stress is the relationship of force over area, cross-sectional area. So force also you can see is load. So we don't have the force, we don't have the load. We do have the area we can measure on the aircraft, but we do not have the load and force, then you cannot calculate the stress. So we have to reverse. You have to calculate the load. We have to determine the load. Only OEM will have the information on the load. Only OEM will have the details information on loads of each structure members. If you know OEM, you do not have that because OEM are the one designing the aircraft. They have the information on every piece of the aircraft structure in terms of load, stresses, factor of safety, margin of safety, everything. And also they show you in the manual. You have all these are in the stress manual of the OEM of the aircraft model, and then in that manual also they give you the methodology of doing the stress analysis. So we have all the detail. If you are able to get hold to those manual, then your life will be easier. Unfortunately, as we are working for the airline, we work for the MRO. We do not have that privilege unless you are a very big airline and you are MRO for the OEM. Possibly you will get the information. If not, then we do not have access to that. And if you do have access to that, your life will be very easier, and you do not have any approval from authority because that document has given you all the information for you to make decision, and any decision based on that manual will be deemed to be acceptable or approved by authority. Okay. So by not having that information, we have to develop the load ourselves. We have to determine the load and we have to do the stress analysis ourselves based on the load. Before we go into the detail, we go into looking at what would be the potential failure. Let me show you aircraft structure. Okay, let's have a look at this. So for aircraft structure, you can see we have here is frame, we have stringers, this one is frames, and we have stringers, and we have skin. So this is typical construction of an aircraft. So how they do connected? They connect those by rivets, and how the connection we call it join. For example, if you want to have, this is frame cross section L, this is another frame, and then we have skin that attached to the frame, skin attached to the frame, and then we install rivets. So rivets in this frame joined together by rivet as well. So that kind of construction. You may also see U channel, and then we have skin over, and we have rivets. So this is typical where we have rivets. To join the structure. So we consider this as join. Yeah. Why join? Because we need to use rivet to put them together. Rivets, 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 and we have rivets. So we call this as join. And then we do have join. If you have join, we do have join failure. So how the join can fail? And we can fail in several ways. The joint, the skin itself may crack through. The rivets may shear out through the skin. You may have crack over the edge distance in both ways. Or you may have squashed the hole of the fastener from round become oval, which is bearing. Or maybe the head will be pushing through, mean that the fastener head will cut through the skin. So this is fastener pull through. Also, you may have the situation where the rivet itself been cut off, like you scissor them off. So cut into two. So those are shear. So here is net tension, shear out, cleavage, bearing, fastener pull through, and fastener failure. It can occur on the skin, it can occur on the frame, it can occur on any structure members, and on any type of structure, including composite. However, composite may have different failure. The failure, uh, the failure philosophy is the same. However, the characteristic of failure may be different. You may not be able to see probably shear out totally like this. They still have shear out issue. May have some cleavage, but may not be that clean. And we may have problem with bearing. I mean, a lot of problem on composite is bearing because of the fastener squashing against those again the hole which been drilled through the composite. That's why most of the composite they're using sleeve to protect the hole from being squashed by the rivets, which will cause the bearing failure. Okay, any questions so far? This is one of important aspect in designing of aircraft structure. After you design the repair, you have to do analysis on the repair, and analysis on the repair, most of it on tension, shear, bearing, and fastener shear. So we most of it we have this failure, this failure, this failure, and this failure. For this, cleavage and fastener pull through is not common, so we'll leave it aside first. We focus on the four. Also, there are like rivet bendings and fastener bendings. We don't go to that because this is actually the fastener is designed to take up the shear. If you have bending issue, when you have already problem on the thickness of the plate that you design. If you have a very thick doubler, then there is already provision for you to reduce the thickness by installing a stainless steel doubler, AISI 301. So if you still have very thick and you're not sorting it out by alternative given by the manual, by OEM through manual, then that's already a violation. That's already a problem in the design. So that's why I didn't go really into rivet bending and things like that, because if you do the manual, if you refer the manual and doing the design, you may not get into that situation. However, tension, shear out, and bearing and fastener shear, that is very common. Any questions so far? If not,
No, sir. No, sir.
and okay, then let's look at tension first. Okay, you may have a tension here. So you may have series of uh, rivets. Give a big skin, and then you have a joint with another skin. You may have rivets. You may have rivets. Yeah. Many rivets. And you have many rivets. Okay, the potential failure of this rivet is the potential failure. This is a potential failure of this area will fail along this line compared to this area. Why? Because this area is already smaller. As you drill the hole, the area, cross-sectional area left is less. So we have here, 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 and here, and here, and here, here, and here, and here. So we need to minus the hole because it's no longer any material there. So if we go back to the analysis of stresses, of stress, which is force over area. So the area that we talk about is this area. Okay. If we compare to this area, This area is bigger because no hole. This area is less because already having the hole, which only left with area between the fastener hole. So as the area become less, the force here remain. We don't change. Because if you design the aircraft, whatever you do, you design to that force, the force remain. It will not change throughout the aircraft operation. Now, if the area become less, the stress become higher. If the stress is too high, this is stress and strain curve. You see the stress and strain curve, the stress will grow into a point where it will break. So if the stress here, higher than this point, and then this area will be broken off. And that is, you see, Aloha Air, how it failed. Okay, you can see Aloha Air, Aloha Air. Okay, so the skin here is a lap splice, all torn off. Okay, because lap splice, we have big joint, long joint, and you have another skin, and we have rivets. Because of fatigue problem, crack grows across. That's why we have this part is broken off. We want to look from the side, how it looks from the side, skin, and we have rivets. And all these are joints. So this is okay. Any questions so far? Okay, for this, how to do the analysis? We take a portion of this, okay, in between half, and then we take out, become this. So we see whether the force is able to cut off the skin between here to here. Let's say we this for this situation. Okay, now you clear. Okay, let's do the analysis. So, let's do the analysis. So we use, okay, let's do this. So we talk about that lap splice and we say, okay, this joint here, let's say it is 3,500 Newton as a force. there's a force. Then this is 2024T3. Let's say thickness is 2 mm, quite thick already. And then the fastener is 4 mm in diameter. Now you want to calculate, so now you want to calculate the stress. Okay, what you need to do is calculate the stress. And okay, is the material which is 2024 FTU. You calculate, you have to compare with the material FTU. So the question now, what FTU that you use? You will use. Okay, you look at the chart earlier. So this is a failure point here. Are you using this? Are you using here all the time or not? Okay. First step is to determine the FTU. To determine either FTU or 1.5 FTY. Okay. Why? Why we need to look at this yield? You multiply by 1.5. You have to choose which is the maximum. Okay. The problem is why we have to do this, because if this point go very high, there's potential past the point where it can come back here. Here. So you need to check which one is more serious. For example, okay, let's go to the chart. Okay, for this analysis, so this is typical material allowables. We call this as material allowable. And always given by the OEM in SRM or from the material handbook, MIL HDBK 5, which having all type of material listed in the handbook, or the material allowable will be in the handbook, or you can get from SRM. So not to worry about this. In the analysis, even in the exam, we give you this. But you must understand how to use this. Okay, you can see here, this is material 2024 T3. There are more options here, T3, T4. The T here is tempering, heat treated, and the material will be heat treated for the material to be able to be strengthened to what level that you want. So you can design it for material to take up, to carry the loads. Design them to carry the loads. You use temper, you temper them. If you see zero, no tempering in near condition, the FTU, FTY, FCY will be a lot less. If you temper, you can temper to get this FTY, FTU to this value. Okay, now the question here is, we have A, we have B, we have L, we have LT for FTU, FTY, FCY. FSU, FBRU, FBRU, you got also AB, and okay. FCU, only you get A and B, no LT, LTY. And for bearing ultimate, you got H distance 1.5, 2.0. So that either if you have one H distance to say 1.5 or H distance of 2.0. You can see the differences between the strength. So this is strength. Okay, now let's look at what is A. A is, when they did the test to get this value, 99% of the time, look at this situation here, they get 435 megapascal. B, when they did the test, 90%, they got 440 megapascal. So if you want to be conservative, you use A, because many times when did the test, they got this 435. And if you are working on primary structure, yes, you must use this value because this is more conservative. However, if you are working on secondary structure, you may use 440 because that's less conservative, and secondary structure may be less critical than primary structure. Okay, why we are concerned about this? This has impact on the weight. Okay, because we are concerned on the weight. So if you use higher value of A, higher value of FTU, then your thickness will be less compared to lower value of FTU. So here is FTU. Okay. That's why we are concerned on this. Okay, I pause. Any questions? Then if you go into the next one, L and LT. Okay. When you make parts, when you make plate, okay, such a plate, they have ingot, they call it, either block of aluminium. They will melt it, semi-melt, and then they roll it. The roll will be just like your paper. Okay, roll. And if you spread the roll, you have the skin. Sorry, it is reverse. So they will make a skin through to the process. It will have a plate or sheet, and then this plate and sheet will have a direction of the grain. So the drawn direction here is L, and the direction 90 degrees to it is LT. L, LT. So you can see L here is 435. LT is 405. Why? Because as they make the piece here, the grain direction is along this line. So you put a load here, obviously it's stronger than if you load this way. This why you got two different values. Just hold on for a while. Okay, I'm back. So here, that's why we have value L and LT, because of the orientation of the grain, orientation of the material. So if you have extrusion, this is skin. If you have angle, say L angle, very simple L angle. L angle also behave the same. Okay, L angle. Sorry, my drawing is not good. Sorry, another one. Okay, we have L angle. Okay. So it's the same. Here is L. Direction here is LT. So this is L, and this direction will be LT. Okay, any question on that? That's why you need to make assessment whether you need to use A or B, L or LT. You use A for primary structure, B for secondary structure. So you can see it's a bit conservative here. L and LT, if we know the grain direction, we know the grain direction, we know the direction of the L and LT, and we are able to instruct the mechanic to cut the angle or to cut the plate for the doubler into, by able to cut and able to orientate the L into the load. If not, then we have problem. Quite a lot there. It's a 35 megapascal. Therefore, we are not concerned about the weight because we're doing repair. We are not really concerned on the weight because the repair also not very big unless it's major repair. Most of the time, we in the technical services or engineering design for repair, we use the conservative. In this case, it's 005. For FTY, we use 270. And then for FCY, we use 310. And then we use 255. Here, conservative, we consider 715 because you consider not enough 2D. And here we use 505 and 605. And for the strain, we use this value. So that's not rule of thumb. This is not mandatory. However, we wanted to have less problem by questioning by the authority, questioning by OEM. We use the conservative value as far as the strength. However, we may encounter depending on the size of your repair. If we become very conservative everywhere, then maybe the weight of the structure is become heavier. Questions? Okay, now let's go back. So determine the FTU or 1.5 FTY. If you go back to the chart, or if you're talking about 2 mm, so 2 mm thickness here is L, and we consider LT, the FTU is 405. Sorry. So we use 405 megapascal or FTY 270 1.5 times FTY 270 megapascal. Okay. Then what do you get? I think 405 megapascal, or you multiply 1.5 to 270, you will get also 405. Identical. So for this situation, we use 405 megapascal. That is the critical failure stress. Tension. So whatever you do the analysis, compare the stress you get from the load here, you compare to this. If the stress that you get here higher than this, it will fail. Because I said that 405 basically, this is the point here. Questions? And then how to calculate? Any question? No? Okay. Calculate the net tension, stress, tensile stress equal force or load time area. Cross-sectional area. So cross-sectional area of this. So uh, okay, so mean that equal 350 3,500 Newton the time. So say the width here 50 mm. Okay. And 50 you have to turn to meter. That is must. If not, you got it wrong. Because the unit engineering meter. 5,000 minus the whole here, which is 4. You time the thickness, which is 2 over 1,000. So you get 5. So never mind, if you have to do this slowly, one by one, because that is expected in you doing stress analysis report. Expected to do this step by step. Return 3500 Newton time 0.05 minus minus 4 mm. 4 mm in meter will be 0.004 meter time. Sorry, not time. Divide. Sorry, I was mistaken. Divide. Okay, divide. Sorry. So this whole, the whole section here minus the whole time the thickness. So thickness will be 0.001 meter. What do you get? 3,500 divided by 0.05 minus 0.004 time 0.001. So you got 76086.956.52 then over meter which is Pascal. Okay, meter square is Pascal. So equal 76 mega, because 10 to the 6 is mega. 10 to the 9 is giga, so megapascal. And then you compare, this is less than 405 megapascal. And you can calculate the margin of safety by 405 megapascal. You must go higher because this is strength 76 megapascal. Get 405 bahagi 76. You got 5.3, which is higher than 1.0. Okay, that is analysis of the net tension failure. Any questions? And I expected you to do this in your exam, in your quizzes, in your assignment, because that is how we do in engineering report. We have to do step by step and have to explain every detail of the analysis. And this report will be read by the authority, will be read by OEM, and that's how they will approve your repair. The repair approval is not just looking at the drawing, they also, the most important thing, they will look at your justification of the stresses, your stress analysis on the report. Questions?
No, sir.
Sure, everyone okay? Everyone can follow? Anyone lost? Totally lost? If you totally lost, you're shy to ask question, just WhatsApp. This WhatsApp channel for you to be able um, to engage with me in private. This is very important because you can see with this kind of analysis concept, if you got the first line wrong, everything will be wrong. Then that's why most of the exam you will get actually most, to be honest, most of it fail. They only able to get through because of your 60% what I call it, your carry mark. Okay. Any question? No. No, then I proceed to
No,
the,
sir.
okay. And imagine you have wrong repair, you may end up with this situation and someone will get killed. That's why you need to really understand to do this before there are any accident. People may get killed and you can be jailed because of negligence. So be careful. You have to understand all this, otherwise you will end up in very difficult situation in your life. So as a as an engineer, as a professional, you must know what we're doing. You must be competent on doing it. Okay, next we look at the shear out. Use the same material, same, the force still the same, You consider everything is the same, only different analysis. Okay. Okay. And material the same. Alloy 2024 2 mm thickness and 4 mm diameter rivets. Okay, now we're talking about shear stress. Shear. So shear is FSU. We have to go back, look at the table. Okay, we look at the table. FSU is 255. 255 meter square. F shear stress. Okay, now you have to calculate the stress. Calculate the stress from the 3,500 Newton loads on the plate or on the screen. And compare with the okay that value failure stress. So how you do want to calculate the stress on shear out will be load time shear area, which load equal to 3,500 Newton. Shear area will be thickness time each distance time 2. because we have consider shear out, then there's one area here to shear. So this is second area to shear. So that's why we time 2. Before 3500 Newton. Sorry, I forgot. I make mistake again. It's not time. It's divide. Okay, divide by thickness 2/1000 to mm. Have to change to meter. Time is distance 2 time diameter 4/1000 meter, and everything will be time 2. So 3500 Newton divided by 0.002 sorry 0.002 meter time 2 time 0.004 meter, and everything will be time 2. Okay, so what do you get? So the whole thing will be 2 sorry, not 2 here. Okay, 0.02 thickness, 0.002 thickness time each distance. Why each distance? Because each distance is distance between here to here. So this is the length of the shear. So this one the each distance. So this distance is by rule we have learned before is minimum 2 times diameter of the rivets of the hole. So this is 2D here. So we have this here 2D. This is the thickness. Then time 2. So 0.002 time 2 time 0.004 time 2. So you got area equal 3500 Newton divided by 0.00032 meter square. So what do you get? So 3500 divided by 0.00032. You got 109,375,000 Newton meter square, which is Pascal. And then we are into the 09 mega Pascal, which is S and 255 mega Pascal. Margin of safety will be 255 mega Pascal divided by 109 mega Pascal, which is 255 divided by 109, you get 2.3. 2.3, which is higher than 1, mean there is no failure of shear out. Can you follow?
Boleh, sir.
Boleh, then you guys will score lah. All this in the exam, summon, everything, we use this lah. Okay, next we look at the after shear out bearing. So bearing. So bearing, we use the same. Force remain the same because same design, only different analysis. It is 2024 P3 thickness 2 mm. Diameter rivet 4 mm. Okay. So we go back, here is bearing, you go back to the chart. It's bearing ultimate, bearing yield. So let's see, we use bearing yield. H distance 2.0, so we use 605. So we use 605. FBRY 605 megapascal. So we calculate bearing stress equal loads over bearing area. So load equal 3500 Newton. Bearing area is very simple. Thickness times diameter. So 3500 Newton divided by thickness, which is 2 over 1000 to change to meter, times diameter, which is 4 over 1000 meter. So 3000 100 Newton divided by 0.002 meter times 0.004 meter. It is 3500 divided by 0.002 times 0.004. So you got 437 500 000 Newton meter square. Meter square, which is, so we get 437.5 mega. Margin of safety 605 megapascal divided by 437.5 megapascal equal 605 divided by 437.5. 1.38. 1.38, which is higher than 1.0. So there's no issue of bearing failure. First, you can see here the bearing stress is only 437. The material bearing strength is 605. Obviously, it's not reached that, it won't fail. And continually evaluating the margin of safety, you can see the margin of safety is more than 1. So it's no potential failure of bearing. Any questions?
Sir, sorry.
Hmm.
Nak tanya yang FBRY tu apa maksud dia, sir?
Bearing yield. Bearing ultimate, bearing yield. Bearing ultimate, the material fail already. Bearing yield is material start to go into the plastic region. Mean after yield, the material will deform permanently. You can
Okay, sir. Thank you,
see the
sir.
table. Okay, you can see the table. Table here show FBRU, bearing ultimate, FBRY, bearing yield. Okay, and then bearing ultimate for either UED is 145, ED 2.0. Similarly here, yield ED 1.5 or ED 2.0. Because in fact the SRM has given the worst scenario of having 1.5D, not less than that. But you cannot have 1.5D for countersunk, because actually if you allow 1.5D for countersunk, it's less than 1.5. Most OEM allows you to use each distance of 1.5. However, the best is 2.0. Then we have to do the analysis. That is how we design the structure repair, but we have to continue. We have to support by the analysis, just like what we're doing now. Okay, next, let's look at shear. Any structure fail of the reverse shear off, especially after the structure experience overload. For example, when they have emergency landing. So there is a severe overload on the structure. You may see the rivet heads just pulling off. So what is shear now? Shear is the cut. They cut the rivets into two. So here is a plate. If the plate have a higher force, the plate can be just like scissors. They will cut off the rivets or the fastener into two, into half. Most of aircraft structure, large transport aircraft, they use lock bolt. Those are stainless steel pin. So here is stainless steel. But rivet, we still use aluminium. For example, 2117 aluminium. However, for this analysis, just to keep things simple, we may still consider the same the aluminium made of 20243. Okay. So for this situation, everything are the same. Like I say again, this is analysis of the same design. 3,500 Newton. And this one is 3,500 Newton. Pull and still shear. So we can say rivet shear, single shear. Because no other plate, just two plate together, those are single shear. Equal load time cross shear area of the rivet. Okay, so what is load? 3500 Newton. Sorry, I always make mistake. Not divide. No, it's divide. Sorry. Division. Divide by cross sectional area is pi time radius. You have to square them. Okay. So 3,500 divided by pi r square of the rivets 3500 Newton divided by pi r square. Only this square is the radius only. We don't square the pi. So 3.14 time radius, which is diameter 4, radius is 2. Square. Okay, so 3500 Newton divided by pi r square 0.002 square times 3.14. You got area 2 over. Okay, 2 over 1000 square times 3.14 is 0.0000.256 meter So you got the stresses of 3,500 divided by 0.662 Newton over meter square, which is Pascal. You can say 279 megapascal. It is, if we consider same material, which is not happening, this is different material. However, just for the sake of this analysis, we say same material, which the shear of 2024 is 255, which is less than 255. It is more than 255 megapascal. So margin of safety will be 255 for material divided by 279 equal 255 divided by 279 is 0.91, which is less than 1.0. So we can say the rivet fail, the rivet will be shear off. Okay. However, for 2117, if you can Google alloy 2117, which rivets made, rivets. Shear is 0.93. 190, even less. Okay. Okay, anyway, if you look into that, when the shear due to this force cause stress higher than material, yeah, this is what you get. This is shear stress from this force higher than the shear stress allowable on the material, then you have rivet. The rivet, this rivet will be shear off, so it's a fail. Any questions?
No, sir.
Okay. Next, I will explain about the load loss. Because whatever you do, this is joint. Next one, we'll talk about load loss. If we do have damage and angle, let's say that we have crack here, and most of the time, what happened, we will cut off the crack. Yeah. Just like when people have cancer, they remove part of the body. So remove this, and then we install a filler to fill up the space here. So what happened, we already lost area. Here, we lost area. And load equal stress time area. So we already have load loss. So if we multiply, it's a load loss by having stresses time loss area. So you got the load loss. How much loss after you remove? So you look at from the side with a cross-sectional view. So you cut through this section here. What you see, you have no longer having this area. This flange is no longer there because remove. So here the only effective area. So we only have only this area to carry the load. Here we have gone, no more. And this need to be calculated. So this is the loss area. And then you calculate the stress over loss area, you will able to have to calculate the load loss. And then the load loss has to be restored by having a doubler that put over the area, and then we put the reverse. So this is repair. However, for the moment, I do not want to do the repair. We just want to calculate the load loss. How to calculate the load loss is very simple. We just calculate the loss area times the stress. So for this situation, load loss here, okay, load loss by say we carry the same 3,500 Newton. So simplify, say this structure here is load to 3,500 Newton. Then we have loss load. So what we do here, we have to look for the stress times the loss area. So we have stress, remember 405 megapascal, we use that. This is tension. Loss area will be thickness. The thickness here is say we have 30 mm, and here also 30 mm. So what we have lost is 30 mm, which is over 1000. We have to minus this thickness because 30 is from here to here. And you have to minus the thickness here. Say the thickness here is 2 mm. Then you have to minus 2 mm. Then the whole thing you multiply by the thickness, which is 2 mm. And then you got the area loss. Right? 2 over 1,000. So this is meter. This is meter. And then you write the you get the load. Okay, meter and meter will cancel. So 4,500 megapascal, which is 4,500 Newton meter okay, time meter square. 30 minus 0 30 minus 2 divided by 1,000. 0.0028 meter time 0.002 meter. Don't be lazy to do step by step, because the step by step will gain you point, and then will eliminate potential mistake in the analysis. Time 0.002, you got 0.00056 meter square. So you can see here, meter square, you can cancel. So Newton meter square, you time meter square, you can cancel this, and then you got the unit Newton. Then if you got the unit Newton, then you are on the right track. Equal time 405E6 2260 2260 Newton. Okay. This is 405 megapascal, sorry. 405. 405. So the force, the load that you lost is 20,600 Newton. Okay, let's keep it away. So that area carry 2,022,680 Newton. That's lost. And then that's why you put the doubler. The doubler here should be able to take up. Okay, the doubler should be able to take up the loss. So the doubler shall be able to pick up the 20,680 Newton. That's why we call repair is restore. You can restore back the load, and the repair is able to make sure the whatever load that goes through the structure will be recovered. That's why rule of thumb, one gauge sticker. One gauge sticker means it's one thickness thicker than 2 mm, and when you have one thickness thicker, obviously you easily get even higher than 22,600 Newton. We will do that later for the design or repair. However, now we're just looking at that analysis of the joints as well as the load loss. Okay, last one before you leave. We also have a situation where we have loss load. If we got this fuselage, and then you may have crack. So if you explode the view, the area you have removed, you have to remove the crack, you have to cut them off. Okay, you have to, this exploded view, you have to cut off. And when you cut off, you still back to the issue of you have lost the load. But in this situation, it's a scheme, it's not straightforward. So you have to calculate the load loss of the shear here, also the loss due to the pressurized of the aircraft, in the longitudinal load of the aircraft. So you have to consider this. And when you calculate the loss of load to the pressurization, shear along this cut here, and loss of load due to longitudinal load, and shear of here, and then both you have to get the total load loss here will be, you have to calculate the resultant load. What it means is this area, okay, you have to transfer, to make a doubler, to transfer the load along this area. So you have to calculate a doubler that you were able to restore the loss of this load. So the doubler will be big plate here, okay, which will transfer or restore the load that you have. And you can see most plate in structure repair is stapled here, because most load will be carried in here, and this load carried designed due to how much was lost. So most of those loss are here, all the loss are here, and we install doubler to recover the strength of the area, or to recover the loss. So basically we just talking about this area, this and this area. So you put a big doubler, and you easily just chamfer this one off. So because this one does not affect the load carrying capability, it doesn't restore the strength for any of the plate outside this region. Question so far? So
No, sir.
for the loss load is similar. You have to calculate the area. The area here will be the area of the skin. If we do this, the ISO view, so we have the thickness. So in calculating the load loss, you have to have the area. The area that we are concerned, the area that we work on is this area here. Okay, the cross-sectional area. Yeah. Okay. In this area. So this area here, if we say the cutout here is 100 mm, and which is what? 0.01. Convert to meter right away. 0.1 meter. Easier to work. The time we do analysis also easier. Just convert right away. And if we talk about this area is 50 mm. Convert to meter, it will be 0.05 meter. That is the length. between here, sorry, between here to here is 100, and here to here is 50. So what will be the area? Area will be 0.1 meter. If we say the thickness 2 mm, we keep that way. 2 mm is 0.02. 0.02 0.002 meter, 0.002 meter, and then the area will be so we go back to this. So here is what 0.02 times 0.1, you got 0.0002 meter. Okay, so that's the area here. So this area is here, okay, all along here. On the other side, we have area. We have to calculate the area. Area loss. Area equal 0.05 meter times 0.002 meter. You got 0.05 times 0.002, 0.0001 meter. So this is what you have lost in this area here. Okay. Now we have to calculate the force, the loss load. Okay, there's a load loss along this here, which is similar. We have this side. We have also longitudinal loss here. Plus, we also have a shear here and shear here, which need to be considered for us to get the resultant. Okay, we can consider this resultant circumferential. This is resultant longitudinal. Okay, easier load loss for this area here. We can see, let's say this is LC. Let's see, and here we can say shear C, yeah? And here we can say load longitudinal, and here is the shear. So it's simple. Again, load will be stresses FTU time area. So FTU tension we agreed 405 mega Pascal. Area will be 0.0002 meter square. So what do you get? 405 P6 times 0.1232 81,000. 81,000 Newton. And then for the load due to the shear, FSU time area. So FSU will be 245 megapascal time area. So same area here, 0.0002 meter square equal 255 E6 times 0.0002. 51,000. 51,000 Newton. Okay, now, so here is 81,000, and along here we have 51,000. So the resultant load loss will be square root of 81,000 square plus 61,000 square. So square root 81 square plus so 95,718 Newton. So there is 95,718 Newton. So this is the load that you need to consider. This is the load you need to consider in restoring this area by designing your doubler. Okay. So the doubler will carry the load over here. You need to restore the strength of this here by designing a doubler. Doubler will be installed here. I mean, in general, actually the doubler will be covered everything. But where the load is concerned, the doubler of this area need to carry 95,718. That's how much load will be carried by the doubler over this area. And doubler over this area also the same. Here is nothing, is empty. You don't carry anything. Just whatever doubler that you have to cover this, or to cover, only to cover the area. Okay, you can continue calculate this RL here. Similar way. It's already almost 4:30, so I think it's too late already. We can let you go. You can calculate here. So now, what is the point now? What we're doing here is to calculate the load loss of the angle, okay, and or channel, and the load loss on the skin when you do repair. When you cut out the damage, remove the damage, and you do double repair. So this is the method how to calculate the load loss. Any questions?